So welcome to TCP Selective Acknowledgement. Glad to see so many people here and interested in this topic. I'm hoping this is your agenda of why you chose to select this class this afternoon. Hopefully you want to learn more about SACK and how it relates to out-of-sequence packet delivery. That you want to learn more about how out-of-sequence impacts performance, because it does. We're going to see a really great example as part of the session of just how bad can be. And hopefully you want to learn more about using Wireshark to interpret the SACK field and interpret out-of-sequence packets. So hopefully that's part of your agenda. My agenda, what I plan to talk about, is we're going to quickly review some of the relevant RFCs, because everyone here loves to read RFCs. Is that right? Yes. I mean, it is a necessary evil, and you never know when you're going to come across something that really connects the dots. So we're not going to read any. I'm just going to make sure you know about them. We're then going to go into some of the basics of TCP acknowledgement, and that's going to lead us into introducing SACK. We'll do some decodes. We have some examples to look at to help reinforce some of the concepts. And then we're going to share an adventure from the field, which hopefully you'll find entertaining and interesting, and then we're gonna wrap up. So a little bit about me. I work for Riverbed. I'm a performance management strategist. That's my latest title. I get to choose my title, which is a lot of fun. What that means is I tend to help customers look at how can they implement performance management capabilities into the organization to make the organization better and more effective, providing better service to the stakeholders. I've been doing protocol analysis since Token Ring days, Sniffer, Network Advisor, Coax Ethernet, ATM, quite a while. And I love complicated performance issues. I hope you all caught the keynote this morning. That keynote for me was really interesting, as the terms like think about thinking. You know, what thought process do you go through? Easy to solve performance issues. They're not that exciting. It's the ones that are really tricky that really make you think, really pull from past experience and apply different principles and concepts. So for me personally, I love the complicated performance issues. And last point about me is it had to go in 2003. It's now incremental. Every couple of days it pops out and then I have to take it off again. Okay, so that's a little bit about me, the agenda, what we're going to talk about. I want to make sure we finish on time, so I'm going to try to keep the pace going, but I do want to welcome questions. I think we're due to finish at 12:15. Does that ring a bell? Does that sound right? Yeah. Okay, well, it's go time, so let's get started. As promised, a couple of key RFCs. So 793. It's tough reading, but it's important reading. A lot has changed since that was written, but if you ever wanted to go back to say, okay, well, what were the basics? What were the principles? What were the guidelines? What were the shoulds and the musts? It's in 793. Lots of changes since then, but I always like to refer to that one as, I guess, the granddaddy of RFCs. And then RFC 2018 starts to describe selective acknowledgement, which is what we're going to drill into. That was around 1996. There's been some improvements and enhancements to that RFC. And 2883, for example, and it's quite possible that since the year 2000, there might even be some additional extensions, amendments, supersedings. So to get started to drill into SACK, we need to start with making sure we understand the basics of TCP acknowledgement as a baseline. So I'm just going to highlight some of the key key details and make sure that we're all comfortable with these details before we jump into something new and different like SACK. So let's see if everybody agrees with this statement. As long as packets arrive in the expected order, the receiver will /must /should ACK every other packet. That's the default TCP SACK behavior. Does everybody agree with that? Any dissenters? Anyone says, no, that's rubbish? I've got one hand up. It can be configured. So Windows, you can change it in the registry. Linux, you can change it in the stack for Linux. So that the question was, could it be every third? And yes, you can change it, but generally the default out of the box is every other. And then we're going to see some cases where it adapts in a minute. In the case where a packet arrives out of order, the receiver will immediately issue an ACK with the value not with what it just received, but what it was expecting to receive. And that's to signal the sender, hey, I received something, but it's not what I was expecting. It's not in order. I received something out of order. So far, so good? Everybody comfortable with this one? So we're at the basics. I want to make sure these are comfortable for everybody before we go into selective acknowledgement. So key point here is the receiver is going to continue to ACK every packet it receives until it gets the one it's expecting. So we're going to see this ACK every packet behavior until we finally get what we're waiting for. And part of the reason we need to do that is to inform the sender. It's like, hey, I'm missing something important, and I can't do anything with what you're sending me until I get the one that I'm missing. Why is that? Who wants to take a stab at why I can't do anything with what I'm receiving until I get the one that I'm missing? Well, we store it and we buffer it. So that's a good point, but there's another detail I'm looking for. You're saying you can't reassemble the packets? Okay, so another way I would see it, that I would say that, is TCP guarantees in-order delivery. So TCP promises to deliver the data in order up to the application layer. So if I'm not receiving data in order, I can't give it up the stack because it would not be in order, and then I'd be violating one of the key principles. So two key principles of TCP: deliver in order and don't overrun the network. Kind of those two competing objectives. So we're going to keep ACKing every packet until we receive the one that we're expecting in order. So if a sender, so now I'm switching roles here. If the sender, and these words always complicate my brain. If the sender receives, so I'm the sender and I'm getting ACKs back from the receiver. If I receive 4 ACKs with the same ACK number, we call that a triple duplicate. So I've got the original ACK plus the 3 duplicates. So as the sender, if I receive triple duplicate ACKs, then I'm going to retransmit the missing segment. The one that we're waiting for, the one that the receiver is waiting for that's missing. Now this assumes that fast retransmit and recovery is enabled, which is pretty much the default on anything current, any operating system current today. It may not have been default on Windows XP, but nobody runs Windows XP anymore, right? Nobody pays Microsoft a special fee to support it anymore, right? Right. Okay. Everybody comfortable with these concepts? Right. These are the basics that we've got to make sure we're comfortable with as we move on to the advanced topics. So what we've always called ACK has really a special name according to the original RFC, which is Cumulative ACK. So when we see an ACK value in the TCP header here, that's technically referred to as the cumulative ACK, meaning I've received everything up to this number minus 1, in the stream, and I'm now ready to receive the number that I'm telling you. So in this case, ACK 40 means I've received all the way up to bytes 39, and I'm waiting for the byte stream starting at byte 40. That's one of the more confusing aspects of what does ACK really mean. Is it what I've received or what I'm waiting to get? So it's important that we're clear on I've received, on my thumb, I've received up to ACK -1, and now I'm ready to receive the value that's in ACK. Everybody comfortable with that? Is that a surprise, or is that different than what you've heard in the past? Because sometimes that's a surprise. So far, so good? Okay. We're almost to the really exciting part. So enter in a new enhancement to TCP, Selective Acknowledgement. So it was introduced with RFC 2018. And the idea is we want to inform the sender that I've received some of the stream bytes, but not in order. And we want to be able to signal that to the sender so that the sender does not have to retransmit things that I've already received, if possible. So it's an opportunistic benefit. It's not always guaranteed that the sender won't retransmit, but it's opportunistic in that if we get all the signaling right and we do eventually get the missing segments in, the sender won't have to retransmit things that have already been received by the receiver. And so we learn about that through this Selective ACK field. And we're gonna drill in, the rest of the session we're gonna drill in deeply into what does that look like, how is it composed, how do you interpret it. So it's a new option, or it's a new addition rather, to the TCP options section of the TCP header. So the TCP options, thinking ahead back to the original design of TCP, thankfully someone said, well, let's build some flexibility into what we can specify. Even things we don't even know yet might be needed or might be useful or interesting. Let's have a TCP options section of the header where we can plug in things that might have relevance in the future. And so that's where selective acknowledgement was put. We've got timestamps as a TCP option. We've got, what other TCP options can you guys think of? Window scaling as an option, which didn't exist in the original, right? So again, a shout out to the people who designed TCP originally, that they were thinking ahead to a future that they couldn't really envision other than we might need something. So good for them, good for us. So in this selective acknowledgement that we're going to put in the options field, we could define up to 4 separate contiguous groups of segment bytes and signal back to the sender, hey, I'm getting a lot of stuff out of order. Here's the chunks that arrived in order. And we'll look at in detail how we signal that. This last point, because the options field is limited in size, we could do up to 4, potentially, up to 4. But if we're also using timestamps, then we're limited to 3 because we won't have enough space in the headers field to put in all 4 blocks. So we're going to drill down and see what that looks like here momentarily. So how do we turn on selective acknowledgement? Well, it's already on, for the most part, on all modern OSs and up-to-date TCP stacks. And it's negotiated at connection startup time. So if I send a SYN saying I'm going to support SACK, and you send a SYN saying you're going to support SACK, we're good to go, both sides support SACK. And we could independently choose. I could choose to do it, and you could choose not to do it. So the really good news and the intended benefits is that the receiver can now signal back to the sender, not only am I receiving things out of order, I can tell you what those things are. And I couldn't do that in the past with just the cumulative ACK field. With cumulative ACK, all I could do is tell you, hey, I'm missing something. This is what I'm waiting for. You know, hopefully you'll send me what I'm waiting for soon. Ideally, if everything works correctly, we're going to minimize the amount of unnecessary retransmissions, ideally. But you'll see cases where sometimes they'll still retransmit. Maybe it's an older stack that's just not tuned properly, but you will see cases of it. This key point here, ergo the key, and this is really important. The presence of SACK does not necessarily mean that your congestion control algorithms are going to act any differently. They might, but there's no guarantee they will. It really depends on the specific operating system, the version, the TCP stack. But the reason we want to make sure that you anchor on that point is because we're going to see how out-of-sequence packets create performance issues and protocol delays in conversations. So just because we have SACK, make sure that you realize it doesn't mean congestion control is going to work better or differently. And of course, when we do retransmit, and for those of you, hopefully you've had a chance or you will take some of the TCP congestion courses here at Wireshark, because they go into a lot of depth of how those congestion mechanisms work and how they're influenced and why they do what they do. But any retransmission potentially will have a negative effect on the congestion window. So just a quick poll here. So what would tend to happen if there's too many retransmissions from the sender's perspective? He's having to retransmit too much. What would that tend to do to the congestion window? Anybody? Say it again. So we've got slow start as an answer. Anybody else? Shrink it by half, right? Yeah. And that's usually what I see, is shrink it by half until it's so bad that we go back to slow start. Yeah. Okay, so far so good. We looked at some basics. We saw there's a new feature. We're going to drill into that feature in a lot of detail. So it's important that you're able to interpret the SACK field, because it's going to give you an idea of how bad is bad. Like, it's okay to have a little bit of out-of-sequence packets. I mean, it's I imagine a lot of the apps you're supporting are hosted in the internet or hosted someplace where you have to use the internet to get to that hosting facility. So we're using the internet for transport, and it's the Wild West out there. There's no guarantees when you send traffic across the internet. So SACK is really good to help you understand how bad is bad. And when it impacts performance, helping you to make sure that, the reason for the performance problem is actually out-of-sequence packets. We're going to use bytes in flight as our guiding metric. If we see that bytes in flight or in-flight bytes remains high, that means the congestion window has not been impacted. It's not shrinking. We're still able to pump traffic on the network. But if we constantly see bytes in flight dipping down, then we know there's something that's impacting the congestion window. If we see a lot of SACK, then we know it's out-of-sequence packets, and then we can troubleshoot that symptom as opposed to some other symptom that might cause packet loss. Because out-of-sequence packets doesn't necessarily mean packet loss. It just means they're arriving in the wrong order, which messes things up. Okay, does anybody remember this date? I mean, not where you were on that date, but why this is an important date? It's kind of a trick question. Well, this is when Skynet became self-aware. Okay, and the good news is Wireshark is SACK aware. All right, we can decode the SACK fields, we can put them in columns, we can see some of the attributes, right edge, left edge, which we're going to drill into in a minute. So the good news is we've got this new protocol feature SACK, and Wireshark fully supports being able to interpret it, display it, and analyze it. And we're going to be looking at that. So, quick review. Decode summary window. Everybody comfortable with that? Sort of the, actually it's not the default, we've added some columns. So in this particular case, we've added 3 new columns: TCP SACK count, left edge, and right edge. And we're going to look in a minute at some different formats and what those mean. But before we go there, we're going to first point out that if we look at the TCP header here, you can see the cumulative ACK, and that was supposed to be a pop quiz question. Sorry, I gave you the answer. So what do we call this? The cumulative ACK, which says, hey, I've received everything, all bytes, all the way through and including 14.770, and I'm ready and waiting for 14.771. But the receiver is also saying something else. He's saying, oh, by the way, I've also received 1 or more segments out of order, and let me tell you which ones those are. And each segment that I've received out of order has a left edge and a right edge, and we're going to discuss that visually in more detail in a second. And here we can say, okay, well, I've got everything up to 14.770, and oh, by the way, I've also received 17.619 through 19.042. So what's missing? Well, basically from that left edge to that right edge here, which, by the way, is just in rough numbers, a little over 2K. So I'm missing several segments that were transmitted over the network. So the good news is I can see how much is received in order, and I can now see what's been received out of order. And again, we're going to go into a lot more detail about this. So here's an example where there's 2 contiguous blocks received out of order. So you can see the count field now has a 2, and there's a left edge, right edge for instance 1, and a left edge, right edge for instance 2. And by the time we finish this course, you'll look at that and go, I know exactly what that means, because we're going to go into a lot of nice detail. So that's just a zoom into what we just looked at. And you can reformat the columns so that you could actually have one column for left edge 1 here, and another column for right edge 1, another column for left edge 2, another column for right edge 2, which just kind of helps you visually see the extent and the gaps of what's been received out of order. So to do that column change, you just right mouse click on the column header, you edit the header, and you can see there's whoa, that was fun. You can see there's an occurrence field that you can choose. So any Wireshark field that has multiple occurrences, you can choose which one you want to show as a column using the edit column mechanism. It's one of my favorite features of Wireshark, is being able to pick and choose what columns you're going to put on the screen. You know, because different days I feel like a different, some days I wear jeans, some days I wear shorts, some days I want to see SACK left edge, right edge, some days I want to see something else. So it's wonderfully helps me be me, you could say. Okay, pop quiz. What's one of the best things about Wireshark? Go. Somebody. Say it again. Free. Customizable. Knows about SACK. These are all good, by the way. It does some analysis for us. Yeah. Okay, besides the developers. The answer was the developers, you guys. They're in the room next door. No, and honestly, though, the reason I chose to put the developers up there is because think about what they do for us in terms of making this product, extending the product, making it easier to use, helping to make it perform well, etc. So I always like to give them a shout out, for what they do. And they do that, it's a part-time job. I mean, they have their day job, and it's not a paid job. But the other thing that is one of the best things about Wireshark, you guys shouted out just about all of them. It's free, it's customizable. It's the profiles, for me, being able to create your view and your preferences and then save that as a profile. And I'll be uploading to the SharkFest site some profiles that we're going to look at during the session today. So you'll have those available. You can download them, put them in your profile library and use them. Okay, so it's time. Anybody know this artist? MC Escher, right? Crazy. He's a wonderful guy. Let's look at some illustrations now of SACK and these concepts of left edge, right edge, and what all this means. So to do that, we're going to start with a simple example with 5 packets. The sender is going to burst these 5 packets in the correct order, so you can see packet 1, 2, 3, 4, 5. Conveniently, segment length, TCP length of 10 to make the math easy. But unfortunately, there's a network issue. Not like that's ever happened, right? There's a network issue, and the packets are received in the following order: 1, 2, 4, 5, and then 3 is at the end of the train. So now we're going to look at, well, what would that look like if we could visualize and see that? So the first 2 packets arrive. The first byte technically is byte 11, because that's where we started, sequence 11. The last byte is 30, and then packet 4 arrives. And packet 4 starts with sequence byte 41, going all the way up to 50 for a length of 10. So this concept of left edge, right edge, we can see that visually here. So the left edge of this segment is 41, and then the right edge, which would be right here, is actually the same way the ACK field works. It's this number minus 1. So it's what I would be expecting to receive next. So left edge, right edge. And then here comes packet 5, and notice that it goes right where it should, sequence number-wise, next to packet 4, and the right edge has now changed in this gap. So we have cumulative ACK up to here, and now we have this gap of something missing, and these 2 segments are out of order. And we can define the out of order block in terms of a left edge and a right edge. And then finally packet 3 arrives, and now we've got all of our data. So, yeah, go ahead.
What if 3 never arrives?
So if 3 never arrives, then there's other TCP mechanisms that would cause the sender to retransmit it. Anybody know the name of that timer on the sender side? RTO, retransmit, timer, timeout.
What is the differential between this out of order and retransmissions? So in actual, let's say if the packet is dropped, then we are supposed to see the retransmissions?
Yeah, so that's a great question, right? The question was, how can we tell the difference between real packet loss and things that are just wildly out of order? We've got a great example of that coming up in our field adventure, okay? So hold that thought, and don't let me leave until we make sure we talk about it. Okay, so now let's take that example that we just looked at and apply some TCP mechanics to it on the receiver side. So same 5 packets. Packet 1 arrives, and the receiver starts a delayed ACK timer. Everybody happy with that? Everybody agree? Why do I set a delayed ACK timer? Say it again? Well, yes, but what if another packet doesn't arrive? Then we use the delayed ACK timer to say, hey, I got the packet you sent me. I'm happy to receive more if you have more for me. Yeah, but it's nice to remember that when packets come in, if I'm the receiver, one of the first things I'm going to do is set a delayed ACK timer. It's one of my jobs. And now I'm waiting for packet 2. So if packet 2 never arrives and that timer expires, I'll send the ACK. But we're going to see here in a minute that packet 2 does arrive, so I can cancel that delayed ACK timer. Don't need it anymore because the second packet arrived. And now I'm sending an ACK saying, hey, I've received everything including byte 30, and I'm ready for byte 31. So send me that data. Now, because of our network packet, our network problem, packet 3 doesn't arrive. Instead, packet 4 arrives. So what we do is we immediately send an ACK because the packet we received is out of order. So we have to do that. We establish that up front. If I receive something out of order, I have to immediately ACK and tell the sender what I'm expecting. And oh, by the way, since SACK is enabled, we're also going to include this SACK field in our TCP options in the TCP header to declare, hey, I really was looking for this, but instead I received that. Can you help me out? Can you help a brother out? So that ACK goes back, and now the sender is informed eventually, right? Packet 5 is already in flight because we sent these all out in a burst. So packet 5 arrives. It's also out of order. The receiver has to send yet another immediate ACK because I just got something I wasn't expecting. It's out of order. But I'm also going to update the SACK field to put a new right edge on it to inform the sender that I've received this additional segment. So this is the same example we just looked at with pictures, but we're just applying some TCP header fields to it. And this is kind of an important point to keep in mind. At this point, as the receiver, I'm holding on to these 2 segments that I can't do anything with yet. I'm kind of stuck holding them. They're in the bag waiting because they're out of order. I can't send them up the stack yet. They're out of order. So I've got to hold them. And of course, the sender is holding them because they haven't been acknowledged yet. So they're in the retransmit queue for the sender. Packet 3 arrives. Now we can issue Cumulative ACK saying, hey, I've gotten everything up to 60. I'm ready for 61. And oh, by the way, everything's in order. There's no longer an out of order condition. So order has been restored to the force. Now, that one was an easy example. 5 packets, 1 out of order. We saw the effects of the right edge, the left edge. We're going to mix it up a little bit, make it a little bit more complicated. This time we're doing not 5, but 6. We're going to do 6 packets in our burst. And due to that pesky network problem, there's a lot of out of order stuff. So basically, everything arrives out of order. This happens sometimes, not all the time, thankfully, but we do get crazy network conditions, right? Think about a bad ASIC, think about a bad card, think about a bad supervisor, whatever. Things happen that, by the way, I did call Cisco one time, well, many times. I'm sorry, I called my router switch vendor for support. I'm going to say late 90s, right? It was some chassis doing weird stuff. And they said, yeah, it's probably sunspots because there was a sunspot burst, whatever that's called, that happened 3 days ago. And yeah, it's probably sunspots. We're going to have to send you a new card or whatever. I mean, that was a strange one. Okay, so things are out of order. So this is going to be a little more complicated. We're going to put you in the cannon, and then we're going to shoot you out of the cannon, because this will be a little bit more complicated than the last scenario. But the principles are exactly the same, and that's why I wanted to show them. So packet 1 arrives, we start the delayed ACK timer. Packet 3 arrives, it's out of order. So we immediately ACK it and we inform the sender, hey, I received something, it's not what I want, and this is what I received, this segment block. Then packet 6 arrives. Uh-oh, it's out of order also. I've got more out of order content coming my way. And now notice there's 2 blocks being declared. We can declare up to 4, or the receiver can declare up to 4, unless you're using timestamps, and then you can declare up to 3. So in this example, we've got 2. And I'm just going to pause here for a second. Are you guys comfortable with this in this picture? Yeah, so far so good? Okay. So here comes packet 4 now, and notice that what's happened is 4 went right next to 3, and now we've changed the right edge of this block. See how it went from 41 to 51? Okay. 2 to go, 2 to go. Here comes packet 5, so now I've got all of this is a contiguous block, right? And now I no longer need 2 SACK blocks. I can define it in 1, which is 31 through 71. I'm still missing this little piece here. I can't do anything yet with these packets, and I can't send them up the stack until I get the missing piece. So pop quiz time. How many packets are in the sender's retransmit queue? So I've heard all of them, which might be right, by the way. Anybody else?
One, if you see all the selected activity for all the other ones, so you know that the other ones are there.
So we're going to talk about something towards the end called reneging. So a SACK is not a promise, it's informational. Whereas cumulative ACK is a promise. It says, hey, I've got it. Like when we sent this ACK, we said, I've got these stream bytes rock solid. I've got them. So that should have enabled the sender to take that segment out of the retransmit queue. That's my belief. I've never coded a TCP stack, but that's my interpretation. So I think the answer is there's 4. And it's these 4 here. And then the reciprocal, how many packets are in the receiver's queue? Well, I did it again. Okay. I know we can't send these up, so they're in the queue. In the back, sorry?
Will there be 5 in the retransmit queue, though? The one that has not arrived, he's going to be in the retransmit queue as well.
Thank you. Yes. I totally forgot about this missing space here. Thank you. Now, I could say I was just waiting for somebody to make that statement. Good job. So, yes, you're correct. So there's 6 that were transmitted. 5 are in the queue, these 5. This is the one. Now, I want everyone else to think about, why didn't I step up and say that? Good job back in the back. Thank you. Okay. And then packet 2 arrives. Everything is all together. It's all contiguous. We can signal back to the sender. ACK 71. I've received everything up to 70, including 70, and I'm ready for 71.
Question?
Yes.
To go back. So what happens to the receive window in packet 5? Are you going to say it's -10 because there's still 10 in play, or -50?
Right. So let me repeat the question. Your question was, what happens to the receive window as I'm receiving these packets and I can't hand them off to anybody? So the answer is, it all depends. So sometimes you'll see the receive window decreasing. We're going to see an example of that. Sometimes you don't. And I think it's a measure of how much stress the receiver's under and how much memory they have, and the other details, variables around, what OS, what patches, what version, what NIC card, what features, a lot of variables. But we'll see some examples of that coming up. A real life example. Any other questions, discussion before we go a little bit deeper?
So if more than 4, you shouldn't get a 4 or maybe
Yeah, 4 blocks. So you could have,
More out of order?
so that's one of the questions, that's one of my pop quiz questions coming up. So the answer is, what would you do if you were a stack, right? I can't declare anything else. I can't tell you any more information because there's no space for me to signal it. So I think it's like I cannot tell the receiver, the sender.
Because what could be previous behavior that you say
I think so.
So you can't tell the sender, but you've already previously told them, so you can drop the first one, right?
You can't untell them. You can't say, I told you this and now I'm not telling you this anymore.
No, I'm saying, he said, what if you have more than 4?
Exactly. And my belief is that it won't provide any information back to the sender. It'll just say, hey, I received something, because there'll be an ACK, but I don't think any of the information will change. That's my guess. Okay, we shot ourselves out of the cannon. Was that example useful? Yeah. Is it helpful to start with the really simple 5-packet one and then get into something more complicated? You guys good with that? Okay. Because what I found over the years is things that should be easy, the more you look at them, they get more complicated. So you got to try to make it, start with some of the basics. Okay, we're going to move on now to talk about certain firewall effects that you might encounter that could impact SACK. So any firewall admins in the room? 1, 2, 3, 4, 5, 6, 7. Welcome, by the way. We love firewalls. We love security. Do your firewalls do sequence number randomization? We got a yes? We got another yes? Okay, so for the folks that are not firewall admins, what this means is, and this is, in some firewalls, default out of the box, and others you have to enable it, but the idea is an incoming connection that the firewall gets, it'll change the sequence numbers. It'll randomly change it to something random when it goes out the firewall to the server. So now the sender is using one set of sequence numbers. The receiver is using a completely different set of sequence numbers. And if you think about SACK and the cumulative ACK, they're not going to match. And we'll look at some examples. So the receiver only knows what it got after it went through the firewall in terms of sequence numbers. And the sender only knows what it started with before it hit the firewall. And the sender, of course, doesn't necessarily even know a firewall's in the path. It wouldn't need to know. So here's the challenge. If the receiver creates some SACK values behind the firewall, it's not going to match the header. And I'm going to speed up just a little bit and show you an example of what that means. So here's an example where, and these are not relative sequence numbers like we were looking at earlier. These are absolute sequence numbers. So you can see at the header, we're using an ACK that does not match what came from the receiver. And that's because, again, this firewall sequence number randomization messes with the sequence numbers. So when a packet gets to the receiver, it's got a sequence number that doesn't match what the sender sent. I don't know how prevalent this is anymore. And at one point of time, there were firewalls that just didn't try to true up the SACK fields. It's quite possible that the modern day firewalls would actually adjust these numbers back as part of its sequence number randomization. But if you are looking at decodes and you see SACK fields in the TCP options that do not match the cumulative ACK in terms of, I mean, it's not even in the ballpark, right? Then you know there's a firewall in the path, in which case SACK is probably not working in the intended fashion, meaning the sender really can't do anything with this information. It's too far mismatched, right? What can you do with that? It doesn't mean anything. In fact, if I was the sender, I would say, well, these bytes haven't even been transmitted yet. How could they be sacking them? So you'd have to pretty much just ignore it, right? So for those firewall admins in the room, check to see if your firewalls have an option to true up or to support the SACK field. Early firewalls didn't. I've got to believe new firewalls would.
So is it like stateful versus stateless firewalls?
Say it again?
Is it a stateful versus stateless firewalls?
Well, so, you know, that's a longer discussion about firewall features and options, of which, you know, sequence number randomization is one feature out of many. So I think it would have to be something that's stateful, is my guess, because you're paying attention to things like, you know, the connection's open, what state is it in, et cetera. Next up, it's time for our adventures from the field. We have 30 minutes left. A lot of the slides are just click-throughs, they're animations, so I'm going to try to make sure this goes on time. If possible, if I could get a volunteer to give me a notice when we're at 5 after 12, and then I'll know if I need to speed up or if I can slow down. So appreciate, could I get a volunteer to do that? It's not 12:15? All right. Whew, life is good. How about 12:20 then for my volunteer out there? Thank you, sir. All right. You, sir, in the blue shirt. Thank you. All right. So we're gonna look at an engagement I did a few years ago, and we're gonna see some crazy high levels of out-of-sequence packets. Not just a little bit, but crazy high, and what the impact was on performance. So here's our scenario. I was working with a customer. They were in a pre-migration performance testing lab. And what they were doing is they're like, okay, we're on our cloud journey. We need to be able to spin up servers and have those servers download their image from an image provisioning server in the cloud. So kind of a dummy box comes up with a minimal configuration, reaches out to the provisioning server and says, configure me, right? Patches, OS levels, applications, jar files, tons and tons of stuff to make me a real server, right? It's kind of like Pinocchio on the way to becoming a real boy, right? The server comes up, it says, hey, make me real, and then the provisioning server has to download all this stuff. So who's heard of Chef, Puppet? Speaking of Pinocchio, Puppet, Ansible. I mean, there's a number of automation tools that do this. This was several years ago. But the idea was we're going to transfer a ton of content back to the server who wants to be configured. The performance in their little test lab, where there was no latency, was so bad that they had to delay the migration. They weren't ready. And they were on 1 gig links in the test lab, and their first question was, well, John, do you think we should upgrade to 10 gig links? I said, I don't know. Let's look and see what's happening first before we go down that path. 10 gig was super expensive at that time. So you had your typical layer 8 issues. There were multiple vendors. They're all saying, it's not me, it's them, it's somebody, it can't be me, my stuff's working great. There was at least 3 vendors. All of them said, not me, we're innocent. And the customer was left to say, well, I got to figure this out. I've got a date I have to meet. We're making a big bet on the cloud. We got to get ready. So fortunately, they knew about our troubleshooting capabilities. They said, please come in, help us figure out why throughput is so low, and help identify the vendor that's causing the problem. Not because they wanted to kick that vendor out, they just wanted to get them to fix their issue, because nobody was stepping up to fix anything, right? Because they're all saying, it ain't me. So here's what the lab looked like. Pretty simple configuration. There was a server in a security zone IPS firewall. There's some routing between security zones, another firewall, IPS. In another security zone, one called public, one called management, the names don't really mean anything. And the idea was this machine boots up, it says, hey, make me real, and then this server sends a ton of data down. So 1 gig lengths, there's no other traffic in the lab. No latency in the lab, no latency in insertions. And so we had a capture close to this client, and we had a capture close to this server. So there's a session tomorrow called TCP Split Brain, how compare and contrast what the server sees to what the sender sees to what the receiver sees. Highly recommend that course. I know the presenter personally. Definitely recommend that course. And we're gonna in our example here, we're gonna look at some details about what each side of the connection believes is happening and what they're signaling. So we totally used Wireshark, but we also used some advanced analytic tools. And I want to just show you a picture of what we could see from those advanced analytic tools. So first off, what we could see, and this was a random traffic sample, 4 seconds, no big deal, 3.5 seconds. And what we could see from our traffic sample and our advanced analytics was that, well, half of our delay time was due to protocol delay. So things like TCP timers, delayed ACK timers, retransmissions, congestion window closing, that kind of stuff. And in this small sample, we moved 48 meg, there was 117 retransmissions, 49 out-of-sequence packets, and 20 triple duplicate ACKs as part of the fun. So if earlier we said bytes in flight, or does Wireshark call it in-flight bytes? No, bytes in flight. If that number is high and stable, things should be good. Traffic is flowing at a high rate through the network. If that number goes down, then something is closing the congestion window. And if it stays down, that's a bad thing. So if we could graph bytes in flight and see it, so we just answered that question. Wanted to just reinforce the concept of left edge, what that means. And we already talked about left edge. So if we could see bytes in flight, what would it look like if we could graph it? So we're going to zoom into this view. Again, this is some advanced analytics to help understand some of really complicated performance issues. So for brevity, let me just say that these bars down here represent packets moving between two hosts over time. And then this chart is a time series chart of bytes in flight overlaid with the traffic. So you can see this pattern here. It's going up nicely, and then it drops, and then it starts going up nicely again, and then it drops. And someone had a great answer earlier. So what is that called? Slow start. So slow start is good in that it protects the network from being overrun, but it's bad in that it prevents the sender from really putting a lot of traffic on the wire. So it's basically we start back, we have to test the reliability of the network. We send one segment, we wait for an acknowledgement. We send 2 segments, we wait for an acknowledgement. We send 4 segments, and we keep incrementing the burst size, so you can see that happening here, until somehow we decide the network is not reliable, and then we have to scale back. So that's a congestion mechanism in another class, but for this class, we just want to note that there's definitely an impact to bytes in flight. And it's a continuous problem. Remember, the customer called and said, help, we can't get the throughput we need. Right? Why aren't we getting should we upgrade to 10 gig? Well, 10 gig's not going to help with this issue. This is a protocol issue. And then further on in our capture, you can see we never even get back to any good level of bursting. right? We never get back down to 0, so we're not slow starting at this point. It's almost like the TCP stack decided this network is unreliable, I'm going to throttle down, I'm going to stay throttled down, right? So let's see why it's doing that. Any questions before we go look at the why? No, okay. So we're going to use some time-lapse photography to zoom into a burst of 19 packets. Remember we did 5 and then we did 6. Now we're really going for it. We're doing 19. But this is real. These 19 are real. We're going to look at the count of out-of-sequence packets, but more importantly, we're going to look at the nature of those out-of-sequence packets, meaning how out of sequence were they? To what degree were they out of sequence? And we're going to use the SACK field to help us with that. So this is, I think, a great example of how out of sequence can impact performance. And I think part of our job as troubleshooters and network practitioners is being able to help others understand how bad is bad and why is it bad. Because we've got to fix it, and to fix it we've got to figure out, the nature of the issue and who the right party is to fix it. So I looked at, when I was doing the engagement, I had to stare at these packets and these, these decodes for quite a long time. And we're going to look at a lot of detail. And for those of you in the room with glasses, your glasses might need, whoa, I did it again. Your glasses might need glasses for this next segment. So what we're going to do is we're going to drill out to the ACKs. We're going to use the ACKs coming from the client to illustrate the nature of our issue. So here's our ACKs, and we're going to notice some things about these in just a second. So each of those ACKs correspond to one or more of the 19 payload packets, and really I just took a random sample. Honestly, there was tens of thousands of packets. I said, okay, it's impossible to analyze this entire set all at once and make sense of it. Let me just pick a spot, drill into that, and see what interesting might be there. So we're going to use the ACKs to determine the arrival order for these 19 packets. So we're going to do a quick pop quiz before we start rather. So why are there so many ACKs? I thought we're supposed to ACK every other packet. Until that sequencing is restored, exactly. Yeah, so what we're looking at is a constant state of things being out of sequence. I mean, how bad is bad? It was pretty bad. Okay, question 2. Why do the ACK packet sizes change between these different sizes? We've got a 66-byte packet, ACK, no payload. All of them have no payload, 78, 86, and 94. Perfect. So the answer was because the options field is changing size. As we do more of the SACK blocks, the size of the header field increases up to our maximum of 4 SACK blocks. So great answer. Why is the receive window continuing to shrink? Say it again. The buffers on the receiver are filling. Thank you very much. And I can't hand this data off to anyone. I've got to, as the TCP stack on the receiver side, I've got to hang on to it until it can be put in the proper sequence. So we had a question earlier about receive window size. Who had that question? Okay. So you can see it's sort of adaptive, right? Like it didn't change here, and then it didn't change here, and it did not change all the way through here, but then it went from bad to worse. I think it tripped some threshold, and then it started decrementing all the way down from 44K down to 17K, right? So I think it is going to be adaptive, and I think you should expect to see a condition based on the details of the host you're looking at, okay? All right. Why do we see so many duplicate ACKs? because it's out of order, right? Okay, good. All right. Anybody ever take Mr. Toad's Wild Ride at Disney World? Come on, put up your hands. You can do this. Admit it. It was fun, right? So Mr. Toad's Wild Ride is a ride where you get in and you quickly turn left, and then you turn right, and then you turn left again, and then you go straight, and then you back. It goes in crazy directions all at once. So we're about to go on Mr. Toad's Wild Ride. So let's get set for our pre-departure orientation. So we're going to look at a series of 19 slides kind of as an animation. We're only going to talk about each one for about 5 seconds. And the slides are laid out so that we can see which packet has been received, what did the receiver signal, what did the cumulative ACK look like, what did the SACK fields look like. And as I mentioned, each of the slides represents a new packet being received, and we'll also be able to see the state of all the other received packets. So this is I don't know that you can do this with any tool. I did this with Excel and PowerPoint. So here's our orientation. I pulled both captures, put them in Excel, did some merging of certain fields, and then we're looking at the Excel extract of that. So first column is the frame number from the from the host closest to the receiver. So this is the receiver side capture. The second column is the sender side capture, right? And then we're going to put a red box around the packet we're about to talk about. So we're going to say, okay, this packet was just received. Let's talk about it. There's a red box to help us orient ourselves visually. And then packets that we previously talked about are going to be in green. So we can see the state of what's been received, what just got received, what are the header information. And then we're going to see the TCP header as well as the SACK values for each packet that's received. Okay, are we ready to start our wild ride? We're going to need to fasten our seatbelts. Let's focus on our cumulative ACKs and the SACK values. And really the key ask here and the key value is, as we're going through this, challenge yourselves to say, well, wait a minute, does that make sense? Is that what we just talked about? Does this connect the dots? Does it fit the scenario? Or is this totally crazy? Okay. And our starting point for this 19 packet burst is this absolute sequence number. So if you just remember 6095, that's our starting point. Okay, so here we go. First packet has been received at the receiver. So the first packet to arrive is this one out of this group. And after that packet was received, the receiver said, okay, I'm waiting for 6095. I just received something. It's not what I was waiting for. I'm waiting for 6095. And oh, by the way, what I received has a left edge and a right edge of these values. So if you were to track 991 to 438, you would see 991 to 439, because this is the last byte. Next sequence number is 439. So first byte, the first packet that arrived was number 3 of 19. That doesn't sound so bad, right? Surely it couldn't get worse. The next packet that arrived was, I don't know, 8 down, number 8 out of the 19. So in green, just to recap, this is what we just finished talking about, the green one. And the red one is the second packet to arrive on the receiver, which happens to be 3, 6, 9, packet number 9 in the stream. So now our header says, hey, just so you know, I'm still waiting for 6095. It hasn't shown up yet. I got something, but it's not what I want. And by the way, this is what I'm currently buffering. I've got 2 blocks left edge block 1, right edge, left edge of block 2, right edge of block 2. So far, so good? This is sort of like the example we saw before, sort of. Packet 3 received was actually the first packet sent. Okay, so packet 3 was received, and now because of that, we're able to increase the cumulative ACK. So notice this is now changed. I'm ready for 57543, which happens to be the next sequence number, and I still have these 2 blocks sitting in my buffer. Okay, and I'd ask you to guess which packet comes next, but trust me, you'll never guess. You would never be able to guess. Okay, so here comes the next packet in. Notice it's contiguous with this green one, so we don't have to generate a new SACK block. We just need to change the right edge of that SACK block. Does that sound okay to everybody? Next packet comes in. We go back up to here. So now we're filling in, we're able to update the right edge of this SACK block. So it should say 991 to 867, or sorry, 887, and 991 to 887. So that's been updated. I'm still waiting for 57543, by the way. And now here comes something in the middle between between the cumulative ACK and the first block. And now what we can do is really good. We can update our cumulative ACK to say, okay, I'm ready for 887 because this whole block has come together, and now I only have one SACK block outstanding. And if we keep going, somehow we jump again, then we jump back up, then we jump back up, then we jump down, jump up, jump down. Actually, 2 came in sequence, that was cool. Packets 12 and 13. 14, go back up again. 15, go back up again. 16, go back down, go back up, go back way down, go back way up. So now you can kind of see this flow of how bad is bad. And if you needed an example of what's really bad, this is really bad. Remember what it did to Bytes in flight? We couldn't get any throughput through. We got a 1 gig link. We're in the same data center. We've got no latency, and we can't push data because of out-of-sequence packets. And the SACK fields help us. I couldn't have built this table without the SACK fields. And oh, by the way, I'm not interested in building another table like that. This was a lot of like, wait a minute, what am I looking at? So it's been a long, strange journey, but finally all data has been received. So clearly there's a buffer management issue. Would everybody agree with that? Right? Could it be last in, first out? Could it be first in, first out? Could it be last in, first out? Or could it be this? I'm thinking it's that, but I'm kind of iffy about the whole thing. I mean, it's just something really crazy. And by the way, no vendor was willing to dig into the details to figure out, is it me or not? None of them was like, oh, I'm looking at, interfaces are green, no packet discards. What else would they look at? And the reason is because they're not TCP experts, right? Router vendors learn about routing and switching. They don't learn about TCP. Maybe they'll one day be a CCIE for TCP, I don't know. But that's what we do at Wireshark. Not only do we learn about different protocols and protocol features and options, but we also learn about TCP in detail. Questions, comments, thoughts?
That looked like a BitTorrent transmission. Like it was just all over.
Because BitTorrent transfers in clumps, right? Opportunistically. Yeah, this is a buffer issue, right? There was some device in that path of IPS, firewall, routing infrastructure, firewall, IPS. Something in that infrastructure that was changing the order of packets. And the initials start with IPS. Yeah, it's like that. It's chaotic, right? Because BitTorrent does things opportunistically. If there's bandwidth, grab it. If the bandwidth goes away, scale down, right? So the client was very happy because we could help them identify the vendor. The vendor was actually reasonably happy because once they saw the evidence of what it was, they go, oh, you know what? I think I know what that is. Because we could show them visually this crazy buffer behavior. So we talked to the IPS vendor. They went ahead and changed their code. They changed their hardware. They were on a journey to get to a 10 gig box anyway. And we retested with the 10 gig box. There was some improvement, but there was still a problem at even low throughput levels. So they had to go back to the drawing board again and try to keep at it. Because IPS is a really complicated problem, especially at super high rates and tens of thousands of conversations you have to track. Okay, so let's look a little bit about cause and effect. So we can see that clearly it's out-of-sequence packets is a throughput killer. Now this course could have been called, let's deep dive into out-of-sequence packets, but we use SACK to help us understand that, which is why it's a course about SACK. Lots of dependencies, OSs, patch levels. Has anybody ever put a patch on Windows Server and all of a sudden performance tanked because a patch was put on? I mean, this happened. This is real life. This is what happens. Or a patch on Windows or a patch on Linux. There was one customer that put a kernel patch on Linux, I don't remember what version, and all of a sudden it started doing tens of thousands of DNS lookups that it wasn't doing before they put the patch on. So this is the world we live in. This is what happens. This is real life. So dependent on different versions, definitely read the RFC just to feel comfortable with it. Recognize that there's a lot of shoulds and mays in the RFC, which means it's really up to the implementer to decide how much they're going to take on to fully implement a particular protocol feature. So we can see that the sender has impact. I'm going to speed up a little bit so we end on time. The receiver has impacts, like we saw receive window drifting down. At some point, if there was data continuing to come in that was not getting resolved, chances are that something bad would happen to that client. I'm not sure exactly what, but it wouldn't be pleasant. We talked about earlier, there was a question about, well, what if I've already defined 4 gaps and now here comes another out of sequence that requires a 5th gap? So I don't know explicitly if that's called out in the RFC, but my opinion is it's just going to have to not handle it, not report it. It'll have to ACK it, but no changing to the cumulative ACK or the SACK fields. Do you guys remember these movies? Anybody remember the Godfather movie? The Sopranos is a little more current, right? Even though it's retired. But you promise these guys something, you better deliver, right? You better deliver. But SACK is not a promise. And in the RFC, there's something called a renege. Like you can go back on your word. You can say, hey, I'm sacking these stream bytes. And then later on, if you run out of buffer space or conditions change and you can't keep track of it, it's not a promise. It's like, that happened like packets ago. I still need that data. So there is a renege option, which I thought was interesting. So I don't really spend a lot of time reading RFCs, but every once in a while, you pick out a nugget. So what's the impact on the sender's NIC? And it might sound strange to even think about the NIC. Like, why would you even ask a question about it? It's just a dumb old NIC card. But it turns out these days that the NIC cards are mini computers, right? They got CPU, they got memory, they got code, they're running protocols. Are you guys familiar with TCP segmentation offload? Is that a familiar term? There's some other names for it. Large send offload, large receive offload. The idea being you want the NIC card to do the work of segmentation and not the host computer CPU. Now, I think that was probably a misplaced concept 10 years ago, now that we've got GPUs and super fast CPUs in our laptops. But regardless, there is processing that goes on the NIC card having to do with TCP. So this is a question I don't know the answer to. Is the NIC impacted? Well, it's going to have a lot to do on which NIC, which version, which OS, which features are enabled. What about TCP Chimney? Has anybody ever heard of that? Microsoft? I got 2 hands, 3 hands, 4 hands. So TCP Chimney, I don't know who had this brilliant idea, but if you run a packet capture and Chimney's enabled, you won't see any packets. It's like it somehow bypasses some of the OS guts. I don't know exactly how to say it. But if you're on a Windows box, you run a capture and you're getting some packets, but you're definitely not getting lots of packets, check to see if Chimney is turned on. And then the question would be, well, what does Chimney do with SACK? And I have a hand in the back. Oh, thank God. That's good. So the comment was, we believe Microsoft has abandoned TCP Chimney, which if that's true, I'm happier for it. Thank you for that. And then questions about, okay, well, who manages the retransmit queue? Today, mostly it's still the operating system, but what if a future operating system decided the NIC should do that? And there's agreement with the NIC card vendor and drivers, et cetera. Wrapping up here shortly, think about an ESX host where your VMs don't have a NIC card. They have a virtual NIC that's running in software, but the ESX host has a physical NIC card that's somehow supporting all of the connections and conversations on that entire physical host. So it's something you have to consider it. These are things like, there's a book I read once which I really loved called Wisdom Without Answers. And if you haven't read it, it's only this thick. It's a great read. I highly recommend it. So I don't know the answer to that, but I know it's a good question, right? And you may need to know the answer to that at some point in time. Okay, let's wrap up. Some reminders. We can quickly tell if SACK is enabled using a display filter. And I hope everyone here is comfortable or getting more comfortable with display filters. A question in the back?
I just wanted to remind people that receive such coalescence, which will delay the acting, right?
So
Your NIC card has received such coalescence. He doesn't automatically send it up and then the operating system, it waits for an opportunity to interrupt the CPU. So the timing issue changes.
yeah, so
Is that the received TSO?
So there is a received TSO offload, but I think that I think what's being described is something slightly different, which might have to do with, let me keep buffering it until I have a good opportunity to interrupt the CPU and grab the bus. A level of detail we would one day hope never have to think about bus interruption things, but it's reality, right? It's still reality. Okay, so hopefully everyone is getting comfortable with filters and getting more comfortable with display filters. They're very powerful. And then as we saw, we can easily add columns to our view. There's an example of our columns. There's some examples of profiles. We have firewalls that can do nasty things with sequence numbers. So closing remarks, and then we'll be done on time. Really your focus should be on bytes in flight. If that number is good and high, there's really not a performance issue, right? So if somebody is saying there's a performance issue and your bytes in flight are high, that'll require a different kind of investigation, because bytes in flight high means you're pumping data through the path. But if you see the congestion window closing and opening and closing or staying low because of potentially congestion window or receiver side buffering, you're going to want to know how to interpret SACK. You think after an hour and a half I'd know where these buttons are, right? But no, I still have to look at them. It really can be easy to get lost drilling down into the SACK decodes. I don't recommend it like as something to do for fun, but at least hopefully from this course you're comfortable with what's there and what it means and what the interpretation is, and you can do your due diligence of including an investigation of SACK when it's appropriate. And then you can determine how bad is bad, because that's really, I think, what it comes down to. If you have a lot of SACKs with 3 or 4 gaps, then I would say that's probably high or pervasive, and you need to figure out why things are arriving out of sequence. If you only have a few SACKs, you know, with 1 gap each, and it happens occasionally, it's probably not worth a lot of time to drill into that, probably. Supplemental analytics do help, and that's the end of today's session. So thank you guys for participating. Hope this was useful.